All right. Am I bouncing? La, la, la.
You are bouncing.
La. Very good. I will begin. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to just bless our work today, Lord. In your name I pray. Amen. Okay, so we are now in chapter 13 of Dummit and Foote. And so what is chapter 13 about? It is about field theory, all right? So some of these things we talked about last semester, but I'm not, I'll try to go back through them again here since it's been a little while since we talked about these things together. But of course I will probably go at a slightly faster pace. So what is a field? Is what? A commutative ring with identity, right? And we'll typically use F for field in here. Actually, we don't do the double bar so much, just say F as a field. Commutative ring with identity such that what? If U is an F and U is not equal to 0, then what? U inverse is an F, right? Where U inverse is equal to 1, right? In other words, every non-zero entry in the field is a unit, right? And next thing, talk about characteristic. Characteristic of the field, right? Which is also denoted this in Dummit and Foote. And it is defined to be the smallest positive integer, if it exists, for which p times 1, right, is equal to 0. If no such p exists, then we say that the characteristic of the field is 0. All right? Actually, that's not the definition. Well, no, it is. Excuse me. I digress. All right, getting to the point here. Work myself into a corner here. So he points out that we always have a natural ring homomorphism, right? We can look at phi going from the integers into the field, right? And this map is defined by phi of n equals to n times the 1 in the field, right? Now, you remember what this means. This is either just the identity added to itself n-fold times, right? Or this means I'm getting tired of writing this of f. If you don't mind, I'm going to stop that. So it's 1 added to itself n-fold times, or it's minus 1 added to itself n-fold times, right? This defines n times 1, right? Of course, other case would be what? Yeah, 0 if n equal to 0. Anyway, the point is, by the laws of arithmetic, we know that phi of n plus m is phi of n plus phi of m, right? In other words, this phi is a ring homomorphism, right? And it's also injective, right? Well, that's, are we sure about it being injective? We also have this, right? Phi of nm. So for it to be injective, the kernel has to be what? Just 0, right? So as long as the 1 in the field is not equal to 0, it's injective, right? If 1 was equal to 0, anyway, we're assuming that this is not a stupid, I don't know if 1 equal to 0 isn't even a field. I don't care. Let's not talk about that. So assuming that the field is not some really annoying case. Anyway, long story short here, what does this mean? This means that, so the point of all this is, so phi of z, right, is a subset of f which is naturally identified with what? Well, that depends on the characteristic of the field, all right? Well, if the characteristic of the field is p, right, then the way this image works, right, the subset of the field under this homomorphism, it behaves like zp, because if you add 1 to itself p-fold times, you get back to 0. So if the characteristic of f is p, then basically we can think of phi of z as being essentially equal to z mod p, all right? It's isomorphic to that anyway, right? There's a copy of the integers mod p in the field. On the other hand, if the characteristic of the field is 0, then the image under phi of z is what? It's up to isomorphism, a copy of the integers, right? So every field either has a copy of z mod p in it, or it has a copy of z in it by just repeated addition and repeated subtraction of the identity in the field. Either the identity gets back to where it starts, in which case you have a finite characteristic, or it doesn't, you have characteristic 0. Either way, these are your choices. One of these or the other. But then we can build the field of fractions. On phi of z, right? See, phi of z is an integral domain. It's got no zero divisors. It's commutative. So we can do that field of fractions construction that we talked about last semester, right? And so that means that, well, if you build the field of fractions for the copy of, in the finite characteristic case, it's not especially interesting, is it? Because z mod p is already a field, so its field of fractions is itself. Right? Everything in there already has an inverse. But if we, in the characteristic 0 case, we obtain q, right, as the field of fractions of phi of z. But think about it, right? You have phi of z is a subset of f, right? F is a field by assumption, right? And so everything that's non-zero in phi of z has a multiplicative inverse, right? So that means that the field of fractions must correspond to things that are already in f. Okay, so either the field of fractions is z mod p, or the field of fractions is the rational numbers. In either case, we have the following theorem. Field f, a field, has either zp as subfield, or Q as a subfield. In fact, there's more that we can say. This process I've just described of generating from 1 the copy of the integers, or the integers mod p, and then taking the field of fractions. This is the field generated from 1 inside F. And this process I just described is the so-called prime subfield. All right. So to be more specific, every field F either has a prime subfield, which is ZP, or a prime subfield, which is Q. And the prime subfield is the smallest subfield. Smallest subfield. All right, so what's a subfield? F, a field, has extension E if F is a subset of E. And E is a field. And to be more picky, I mean, F has to be a field with respect to the same operations as E. All right? What it is? Have I stated it badly? I mean, I've stated it badly, that's true. But, let's see here. Here, F is a subfield of E. Fair enough, yeah. The smallest subfield of a given field is the prime subfield. You can't go smaller than that, because 1 will generate back the prime subfield. And if you had a subfield, you have to have 1 in there. And once you've got 1 in there, either it's going to generate ZP or it's going to generate a copy of the rationals up to isomorphism. What's the question? Uh-oh.
Is that word supposed to be as?
Grammar.
A field as extension.
F, a field. Yeah, it's has. Liam has solved the mystery of the bad grammar. Well, the first instance of, at least the first instance of bad grammar in this lecture. It will probably not be the last. Let's go on. So also picture. We have K, we have F. So here, F is a subset of K. So that would make K an extension of F. All right, and that's a so-called, F is the base field, K is the extension field. That's a field, tower of fields. Well, you could add more, right? You could add Q down here. Why not? Then that would mean that Q. So F is an extension of Q, K is an extension of F, Q is the base field of F. Anyway, all right. All right, so definition. Yeah.
If Q is the base field of F, would that make Q the base field of K, or would F be the base field of K?
They're both base fields. There's not a unique choice of base field unless you're going to talk about the prime subfield. That's as low as you can go. Otherwise, there could be intermediates. Oh, in this tower, F is an intermediate field. All right. Definition. The degree of a field extension K over F, denoted bracket K colon F, is the dimension of K as a vector space over F. In other words, all right, the extension is said to be finite if the degree is finite and it's infinite otherwise. All right? So, example, if we take K equal to the complex, then over the reals, right? We can think about complex numbers as being an extension of the real numbers. Then the dimension, the real dimension of the complex numbers is 2, right? Because C is the real span of 1 and I, right? And that's a basis. So the complex numbers are a degree 2 extension of the real numbers. If we take K equal to the real numbers and F equal to the rational numbers, it is true that the real numbers form a rational vector space. Because if you think about a rational, think about scalar multiplying any real number by a rational number, it's still a real number, right? You add 2 real numbers together, do you get a real number? Yeah. Right? You go to check the boxes, real numbers form a rational vector space, that's true. And of course, you'd hope that this generically makes sense, because the definition doesn't really make sense unless it's always true that an extension field of a base field is a vector field that makes the extension a vector space over the base, right? If that wasn't true, this definition would be nonsense. So that is always going to be the case because of what it means to be a field, a subfield, right? If you think about what it means to be a subfield, it means that we always have a scalar multiplication, right? If this is the extension field, this is the subfield. If you take 2 things up in here, say K1 and K2, first of all, K1 plus K2 is in K again, right? But if you think about it, F, well, let's use R. R times K is an element of K again, right? For all R and F, because we're thinking of K containing, F. So the field multiplication in K becomes scalar multiplication, viewing the extension field as a vector space over the base field, right? So that this definition makes sense. What's the dimension of the reals over the rationals? What's the Q dimension of R? 1. A little bit off. In other words, I would need a basis, right? You pick any real number, R, and you write it as a sum, I equals 1 to whatever, W for whatever. C, I, qi, where qi are rational numbers, right? It would need to be a spanning set. So any finite linear any real number can be obtained as a finite linear combination of these rational numbers with rational coefficients. You're not going to be able to write down the basis, okay? We only know that it exists by various like foundational set theoretic arguments. I think we need the axiom of choice to select a basis. You can't constructively write such a basis. The answer is infinity. The real numbers are infinite as a rational vector space. You can't find a finite basis of real numbers that build all real numbers as rational linear combinations.
So 1 was close.
So 1 is, I mean, I guess if you take 1, right? I mean, if you take 1 and you just deform it a little bit, right? Like take this and like hook it back there and take that and hook it back there and like, you know, and then twist it. It's 1, right? I mean, up to homotopy or whatever. Anyway. Okay, so not all extensions are finite is my point. There are infinite extensions and they're all around you. Okay, now, so his proposition 2 says if you have a homomorphism of fields, then the homomorphism of fields is either 0 or injective, and the image of a homomorphism of fields is either 0 or the whole field. This was a homework problem for you guys last semester. You remember experiencing this? If you have a homomorphism of fields from F to F prime, the homomorphism of fields is either the 0 map or it's injective. Them's your choices. Because you have to send 1 to 1. Well, either you send 1 to 1 or you send, homomorphism of fields.
You have to send 1 to 1, right?
Yeah.
The ring homomorphism has to send 1 to 1.
Yeah, that's right. So that begs the question of what's ring homomorphism in here? Now you've distracted me. Very well. Let's see here. I was afraid this would happen. So chapter 9 is where he does the, well, maybe not chapter 9. Chapter 9 is polynomial stuff. Probably need to go back to chapter 8 maybe. PIDs. Chinese remainder theorem. I may have gone too far. Euclidean domains. Oh, come on. Chapter 7 maybe is what we're looking for. You're like, you could use the index. That is true, but that would be cheating. Oh, fine. So at the moment we're fussing over what is the definition of a ring in Dummit and Foote, right? That is the question we're actually asking.
Probably just they don't make it include 1. You can look in the index.
Yes, they don't assume 1. Right? Yeah, they don't. No, that's the bottom line. It's on page 239. Hey, look at the index. How funny. You could look at page 239, a ring homomorphism. It preserves addition, it preserves multiplication, but there's no assumption about 1 mapping to 1. So their rings don't have, their rings are RNGs, is what I'm trying to say. They're rung. So with that in mind, you don't have to, I mean, the 0 map is also a ring homomorphism, sort of stupidly so. Okay, let me get back on track here. So everything I've said so far is, I mean, I'm starting to like it. It's starting to be vector space, and it's just my happy place. But this next theorem, I love. I love theorem 4. Theorem 4 is where it's at. Let's see here. Theorem 4 says let p of x in polynomials over the field, f of x, be an irreducible polynomial of degree n all right, over field f, of course, right? And let K be the field f of x quotient by the ideal generated by P of x. Let theta equal x mod P of x. Let me put that down here. In other words, theta, in my usual notation, I would say theta equals to x plus P of x. The ideal generated by P of x, okay? Then 1 theta, theta squared, dot, 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 theta to the n minus 1 form a basis for K as F vector space. So K, the degree of K over F is n, all right? And we here's the characterization of it. What's K look like? K is equal to A0 plus A1 theta plus A2 theta squared plus AN minus 1 theta to the n minus 1, such that A0 through A minus 1 are in the field. In other words, the extension of F is built basically as polynomials of degree up to n minus 1 in this theta. Now this we proved last semester, but it's good to go back through it again, right? What did I call this? I usually call this Kroneker's theorem, right? Now, is there a question? No? Oh, okay. All right, well, first of all, is that a field? Remember that P of x, irreducible, implies that the ideal generated by P of x is maximal ideal, right, in F polynomials over x, which then says that F of x mod this maximal ideal is a field, right? So what do we need to prove here? So what he does is he says let's let A of x be any polynomial over the field, right? And apply Euclidean algorithm to select b of x and r of x and f of x such that what? A of x equals to b of x times p of x plus r of x. So I'm dividing by p. And what is it? No? Okay. Oh, this was on our final exam?
Was it? Something similar was.
I don't know, so long ago I can't remember. Actually, I mean, truth be told, much of what I'm doing right now, you don't even need the irreducibility, you know? I mean, it's still, K still has this structure. If you drop the irreducibility, we can still look at the quotient as having this form where these are independent. It's just that it's no longer a field. It's some sort of ugly ring. And I asked you guys various ugly questions about these ugly things. But we are more focused on fields this semester, so the zero divisors are behind us. Yeah. Go for it.
So the parentheses mean the same thing as the angle brackets, right?
Right. Yes. Okay, so what can we say about this? Where the degree of r of x is less than n, or r of x is equal to 0 straight up, right? And notice that a of x is, well, it's congruent to r of x mod p of x, right? And when you write something like that, you wonder, what does it mean? What that means, of course, is that a of x plus the ideal generated by p of x is equal to r of x plus the ideal generated by p of x, right? Because the difference of a of x and r of x is what? It's b of x, p of x, which is where? It's an element of the ideal, right? So those are different representatives of the same coset, which means that they're congruent mod p of x. And if we let theta equal to x plus p of x, then what? Phone is misbehaving. Then what? Well, let's see here. Theta squared is what? I mean, theta squared would be x squared plus p of x and so forth. I'm sorry, I'm wandering here. Let me get back on track. Let's see here. He says, so we've already shown that every residue class in f mod p of x is represented by a polynomial degree less than n. He says, hence the images of 1 theta, theta squared, theta n minus 1 of 1 x, x squared up to x minus 1 span the quotient as a vector space over f. So his claim is, from this, it's then clear that theta, I also want 1. 1 theta, theta squared, theta n minus 1 spans K. Does that make sense to you guys? So if we If you pick anything, yep.
That statement makes sense, but how do you know that from what you showed?
Okay, so let a of x plus p of x be an element of k, yeah? Then a of x plus p of x is equal to r of x plus, I am getting really tired of writing this. If you'll forgive me, I'm going to call that I. And lingle wringle is just as bad. You like it better? You just want me to say lingle wringle, you monsters. So r of x degree n minus 1 means I can write it as a0 plus a1x plus da 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 plus an x to the n minus 1. All right? Plus I. But then by properties of coset, by properties of by coset arithmetic, this can be rewritten as a0 plus I. More to the point, it can be written a0 times 1 plus I plus a1 times x plus I plus plus an x to the n minus 1 plus I. Yeah.
Should be an minus 1, or is it?
Oh, that's an an minus 1. Yes. Thank you. And that, furthermore, can be written as excuse me, 1 plus I, a1, well, this is theta, right? And the next one would actually be a2x plus I squared. So this may not be obvious, but you can move the power outside. That's one of the properties of cosets if you look at it here. If we, right? If you don't believe it, work it out. Anyway, so what you're looking at then is a0 plus, well, a0 plus I, fine, plus a1 theta plus plus a2 theta squared, da da da, plus an minus 1 theta to the n minus 1. And so if we agree to suppress the coset for the constants, right? If we agree that we're just going to abuse notation and replace this a0 plus I simply with a0, all right? Then we got it. We've just shown that a of x plus, well, fine. Don't leave it like that if you want. I mean, I can leave this as a0 times 1 plus I. I'll tell you what we've actually shown. All right. A0. We've shown that a of x plus I is an element of the span of 1 plus I. And then theta squared, da da da, theta n minus 1, yeah? And those are coefficients in F. So I warned you guys last time. We say that the subfield has to be a subset, but we don't really put that into practice. We're content to have a subset which is isomorphic to the given thing we're extending. So the isomorphism that I'm talking about is just the assignment of 1 to 1 plus I. You know, so we just drop the I and say 1 there. Yeah.
Well, and could you write that as, you could write 1 as theta to the 0, right? And then it would, the x bar would be put outside of parentheses.
If that makes you feel better about it, I don't know. I mean, it's there. Technically speaking, K is a set of cosets, right? I mean, it's a set of, polynomials plus this ideal, right? 1 is not in there, technically speaking. But 1 plus I is, and 1 plus I behaves as the 1 for the quotient. So I'm just saying we can identify 1 and 1 plus I, and we're going to do that. We did it last semester. Eventually you guys got used to it. Now I'm just trying to confuse you again. Did it work? Okay. So up to confusion about notation, I think we have spanning. And then what's next is we need to show that it's linearly independent, right? So to check linear independence, all you do is look at B0 plus, and now I'm using it already, Liam, B1 theta plus B2 theta squared plus plus Bn minus 1 theta to the n minus 1. Set that equal to 0, right? Testing for linear independence, we need to know, we need that all the coefficients B0 through Bn minus 1 are all 0, right? And the proof is simply this. If we had b of x defined in the, well, let's say g of x defined in kind of the obvious way, right? This would be a polynomial in f of x, right? Because all the b's are in f. And what would this have? What would g of theta be? By assumption, right? So he points out that this polynomial would be congruent to 0 mod p of x. Right? So this would say that g of x is congruent to 0 mod p of x. But what would the problem with that be? I mean, that's what this equals to 0 means. It means that it's a multiple of p of x. Let's just focus on that statement. G of x, a non-zero, a multiple, what did I just say? Grief. So we have a polynomial of degree less than n, which is a multiple. A polynomial multiple of a degree n polynomial. Is that possible? Can you have a degree 3 polynomial, a multiple of a degree 4 polynomial? This is not possible, right? So if the b of x was, if the g of x rather was non-zero, we get a contradiction. In other words, it has to be the 0 polynomial, otherwise it doesn't make sense. And so that's the linear independence. And so that is really the fundamental building block for a lot of what we do going forward this semester, because we're always looking at polynomials and building things by quotienting. At least that's the construction of a lot of things. So we will spend more time in 13.1 after the test. I mean, I want to make sure we have 13.1 really nailed down solid before we go on. So I'm sorry if I have not done it justice today. I tried. So you can hit the record there. So